It's by Vicky Hoskins from Radboud University, Nijmegen. And the title is Motives of Moduli Spaces or Bundles on Curves. So please, Vicky.
Well, thank you very much. And thank you very much for inviting me to speak here. Yes, so I'm going to talk about some joint work with Lehalleur and Pepin Lehalleur on motives of various different bundle moduli spaces, all on curves. And the goal of this project is really to understand the geometry of these moduli spaces by understanding their motive. So let me just start with an overview of what are the moduli spaces that we're interested in. For me, C is going to be a smooth projective curve, which is assumed to be geometrically connected over an arbitrary field K. And I'm going to fix a rank and a degree D for my vector bundles that I'm considering. Then I have various different moduli spaces that I want to consider. So on the top left, we have the most classical one, the moduli space of semi-stable vector bundles on C. And this is a projective variety, which it can be constructed by a GIT or gauge theoretic terms if you're over the complex numbers. And it's smooth when semi-stability and stability coincide. So that's when the rank and the degree are coprime. And also, occasionally, I'm going to want to consider the moduli space with fixed determinant. So I'm going to denote this by NL. And then moving this way, we then have a sort of hyperkähler version, which is the moduli space of semi-stable Higgs bundles. So this is no longer projective, but it's a quasi-projective variety, and it's still smooth when the rank and the degree are coprime. And it's got twice the dimension of the moduli space M. Then moving downwards, I want to consider some sort of parabolic structure. So I will talk about exactly what is parabolic vector bundles later on in the talk. But firstly, we can consider moduli spaces of parabolic bundles. So, and these actually depend on a notion of stability. So unlike for the classical moduli space N, where there's just basically one notion of stability, here we have different notions of stability given by a stability parameter alpha. And these give rise to different moduli spaces where, so essentially the idea is that you have a collection of parabolic points, and at each of these points, you're asking for some sort of a flag with some prescribed multiplicities. And again, there's also a one with fixed determinant. So I've written that here. Again, this is still a projective variety once we look at these parabolic structures. And it's smooth when semi-stability and stability coincide, so if alpha is generic. And then we can also pass to the hyperkähler version, which is the moduli space of semi-stable parabolic Higgs bundles. And again, this isn't projective, but it's quasi-projective. And it's smooth when alpha is generic. And so the goal of this project is really to describe the motifs of all of these moduli spaces to capture as much of their geometry as possible. And so I want to say what I mean by motifs here. So I mean motifs actually in the sense going back to how Grothendieck originally envisaged motifs. So in terms of algebraic cycles, so via Chow motifs. And this in particular will encode various cohomology groups. So for example, singular cohomology together with, well, so actually I guess, basically everything is going to be a pure Hodge structure, and also L-adic cohomology and Galois representation, and also algebraic cycles. So this motif will also tell us about Chow groups of these moduli spaces. Okay, so I'm going to start with an introduction to Chow motifs. So the construction is, we start with the category of smooth projective varieties over a field K. And then we sort of Q-linearize this in a way by looking at correspondences over K, which has the same objects, but now the Hom groups are given by Chow groups of algebraic cycles up to rational equivalence. And then you construct the category of effective Chow motifs by taking the idempotent completion of this category. So the objects in here look now like X, a smooth projective variety, and P, an idempotent element. An idempotent endomorphism of X. And again, Hom groups are given by Chow groups, and then you have a pre and post composition with these idempotent endomorphisms. And so putting this all together, going from here to here, we get a functor which is written as H here, which is a symmetric monoidal functor. And it sends a smooth projective variety X to its motif, which we'll just write as Hx here. And it's monoidal, so it sends the Cartesian product to the tensor product of motifs. And the unit for this tensor product is the motif of K, which is written just as Q0. And the motif of P1 actually decomposes. Firstly, we have the motif of the point, and then we have another motif, which is an example of a Tate twist. So this is often called the Lefschetz motif. And these are all these higher tensor powers of this feature as direct summands in the motif of Pn, in the sense that the motif of Pn is decomposes into the sum of these different Tate twists. And then actually, I just wanted to say, although we don't really need to use it because always we're going to stay inside this smaller subcategory, that you can actually tensor invert this Tate twist and go to a larger category of not necessarily effective motifs. But I think everything we're doing today, we can stay inside here. So it's not to worry about too much. And so I won't say too much about exactly how you tensor invert this. But one advantage of tensor inverting is that then you can do things like Poincare duality and so on. And for those of you who perhaps seen me before talk about motifs often, I've instead talked about Voevodsky's motifs, which is a much larger category. So actually the category of Chow motifs embeds inside the Voevodsky's triangulated category of motifs. And this much larger category, you can deal with more interesting types of geometric objects. So for example, you can look at motifs of stacks and things like this. So this category is much bigger, but since we're just dealing with moduli spaces in this talk, it suffices to work with Chow motifs. And actually, well, we have to be a little bit careful because actually not everything that we're working with is smooth and projective. So I will talk about how we deal with the Higgs moduli space when we come to it. Okay, so I wanted to say briefly some properties of these Chow motifs. So firstly, they have a universal property that any Weil cohomology on smooth projective varieties factors via this motifs functor H. And then secondly, they encode Chow groups in the sense that if you have a smooth projective variety, then its ith Chow group is just the Hom group in this category of Chow motifs from the motif of X to one of these Tate twists. And then you also have things like projective bundle formula and blow-up formulae. So things that you have for Weil cohomology theories, you also have for motifs. Okay. So I wanted to start by talking about our results on the moduli space of semi-stable vector bundles on C. So this is the most classical moduli space considered by this VBAC group. So the first theorem is, so in this case, we assume that the rank and the degree are co-prime. Then firstly, we show that the motifs of both the moduli space of semi-stable vector bundles and the one with fixed determinant lie in the tensor subcategory generated by the motif of the curve. So actually this is a relatively straightforward adaptation of an argument of Beauville and Bullis, which just uses Chern classes of the universal family. So this isn't really too deep, but we use it in various places because in particular, this tells us that the motif of both of these is abelian. And then secondly, we have that we can relate the motif of the moduli space without fixed determinant to the motif of the moduli space with fixed determinant via an isomorphism like this, where here we see the Jacobian appearing. And so the second point actually refines the isomorphism of Harder and Narasimhan on the level of L-adic cohomology. So if you recall, if we look at the end torsion points in the Jacobian, then it actually acts on the moduli space with fixed determinant by just tensorization. And there's an isomorphism between, so if I take NL cross the Jacobian and then I take the quotient by the natural gamma n action, then this is isomorphic to the moduli space n. And consequently, we get that the motif of n is just the gamma n invariant piece of the motif of this product. And then to conclude, all we have to do is show that this action is trivial. So we already know this on the level of cohomology by Harder and Narasimhan. And so actually we want to, again, get back to that proof. So how do we do this? Well, firstly, we reduce to a field of characteristic 0, essentially by working over a curve over a DVR. And then we show that part 1 tells us that the motive of the moduli space with fixed determinant is abelian. And then in characteristic 0, we use that L-adic realization is conservative on abelian motifs. And so in particular, because we know from Harder and Narasimhan that the action here is trivial on cohomology, we can deduce that the action on the motive is also trivial. Okay, and similarly, the action on the motive of the Jacobian is also trivial, and this is basically because multiplication by n is a gamma n torsor. Okay, so the second proof that we want, the second theorem that I want to present is some formulae for actually the motive. So firstly, we show that any positive formula for the motive of the moduli space with fixed determinant in the L-localized growth and group of Chow motifs actually lifts to firstly DM and in fact Chow motifs. So it suffices to eliminate any negative signs that appear in the Harder-Narasimhan recursion, because obviously there's no way to do negatives in Chow motifs. So you just have to find a positive formula and then this will lift. And this, this first part relies on the first part of theorem A. So it uses the fact that the motive of the moduli space of semi-stable vector bundles with fixed determinant is abelian, together with a conservativity argument. And then the second part, we actually managed to compute some formulae in low rank. So for rank 2 and 3 with coprime D, we get some precise formulae. So in rank 2, I've written the formula explicitly. So we get basically some Tate twists of motives of symmetric powers of the curve. And the symmetric powers range from I equals 0 to G minus 1 here. And so in rank 3, just because the formula is a little bit messy and I didn't want to write it, so it's in our paper, I've just written that instead we get now 2 different symmetric powers of the curve, but again with I plus J less than or equal to 2G minus 2, and then some explicit sum of Tate twists, which I didn't want to write down here, but we did explicitly write these down. And part 2, so in rank 2 relies on work of Thaddeus and Del Bagno, and in rank 3 relies on work of Gomez and Lee. So I'm going to explain the proof of part 2 when for rank n equals 2. So without loss of generality, we can assume that the degree is arbitrarily large by tensoring with a line bundle. And I'll tell you how large we want to assume it is later on. But then we use rank 2 pairs, which were first introduced by Bradlow, and their wall crossings, which were studied by Thaddeus. So let me introduce these pairs moduli spaces. So there's a parameter, a stability parameter, sigma, which is a positive rational number. And associated to each one of these stability parameters, there's a projective moduli space of semi-stable pairs. So we're still looking in rank 2, so we have a pair consisting of a rank 2 vector bundle E with determinant L, so we're in the fixed determinant case still, and a non-zero section of this vector bundle. And this pairs moduli space is actually smooth when theta is generic, so when semi-stability coincides with stability. And there's a very nice wall crossing picture here. So I've drawn the real line, or the positive real line, if you like. And then there's a finite number of walls which you cross where the notion of semi-stability changes. And then eventually you get to some maximal chamber, which once you move outside of that, semi-stability is empty. And so we can relate the moduli spaces on each side of these walls by wall crossing. So let me explain the wall crossings. So actually the moduli spaces on the outside are sort of most interesting to us. So right at the maximal chamber, we have that the moduli space is actually just a projective space. So we understand its motive, which is very good. And then the pairs moduli space in the minimal chamber is actually a projective bundle over the moduli space n that we're interested in. And so the idea is if we understand the motive of this, then we can understand the motive of this. So there is a slight caveat here that D has to be sufficiently large, but at the beginning we said we could take D arbitrarily large, so that's fine. And what happens at each of these walls? Well, at each of these walls, there's a particular type of birational transformation called a flip, which I'm going to say what it is in a second, but they're flips with particular centers, so the centers are always symmetric powers of your curve C. And then the type is basically telling you the size of the projective bundle on each side. So let me give the definition of a flip of type AB. So a birational map of smooth projective varieties is what we call a standard flip of type AB with a smooth projective center S. If there exists two projective bundles which are contained as closed subvarieties in X and X prime, and they're projective bundles over S, such that when we take the blow-ups of these two closed inclusions, we get isomorphic varieties. And the rank of this projective bundle is A, and the rank of this projective bundle is B. And so the notation for this is we write a flip of type AB with center S. And so then maybe I can try and show the picture at the same time. So here you see that we have very explicit flips at each wall, and the centers are always given by symmetric powers of the curve. Okay, so then directly from basically the blow-up formula in Chow motifs, we can actually, at least if we work with the in the Grothendieck group of Chow motifs, we see that the class of X and the class of X prime can be expressed in terms of the class of S, and then basically the difference in the classes of these projective bundles. And actually this is also true on the level of Chow motifs if A is greater than or equal to B. So this is a result of Zhang, and so we wanted to try and apply this result to then compute the motif of NL that we were interested in originally. So I repeated the diagram here, and we start where we understand what the motif is, and we want to go over here. And so we're going to work from right to left, crossing various walls. So at first, it all looks like very good news because we have type AB with A greater than or equal to B initially. So initially, the motif is just increasing, and we can directly apply Zhang's theorem. And so we get that the motif of some pairs moduli space is just the motif of this one, which is a projective space, so we understand it, plus some contributions from these centers of the flips, which are just motifs of the symmetric powers of the curve with Tate twists. However, at some point, somewhere here in the middle, we see that suddenly we start getting flips of type AB with A less than or equal to B. So now what we need to do is cancel part of the motif. And this is something that isn't possible. So because you can't subtract. So instead what we do is we work again in the Grothendieck group. So this computation was actually already done by Del Bagno. And then again, we can use our theorem B, which says that if we can eliminate any minus signs, so we can find a positive expression, then this will actually lift to Chow motifs. And that's precisely what we do. And this gives the formula in rank 2. Okay, so I then want to move on to talk about the Higgs moduli space. So I put a little caution to remind you again that this is not a projective variety, it's only quasi-projective. And so I actually joined just with Simon. We studied this motif a little time ago and showed that it was pure. So in particular, you can think of this motif lying inside this category of Chow motifs or effective Chow motifs rather than in this larger category of Voevodsky. And also, assuming that C has a rational point, we showed that the motif lies in the tensor subcategory generated by the motif of the curve itself. And the starting point for this proof is actually to use Hitchin's scaling action on the Higgs moduli space, which is just an action of the multiplicative group Gn, which scales the Higgs field by multiplying it by T. And this scaling action has two properties, which are what's called a semi-projective GM action by Housel. So firstly, the fixed locus is projective. And secondly, the flow as t goes to 0 exists for all points in your moduli space. Sorry, I don't know why there's a bar over that one. And so this second point allows you to basically deformation retract onto the fixed locus. And then because the fixed locus is projective, this is really saying that the motif actually behaves like a projective, in fact, a smooth projective variety. So this is where we get this purity from. And this actually comes from a motivic Bielaniki-Borula decomposition. So I just wanted to say a few words about what this fixed locus is. I don't want to go into too many details, but I think many people have already seen it here. So the fixed locus for this GM action, there's basically two different types of pieces. So there's one piece, which is the moduli space of semi-stable vector bundles. So that's where the Higgs field is just equal to 0. But if the Higgs field isn't equal to 0, then you get basically a copy of GM inside the automorphism group of your vector bundle, which decomposes the vector bundle into a sum of different eigenspaces, basically. And the Higgs field sends each one of these to the next. So you get what's called a chain. And this leads to then moduli spaces of chains, which are actually smooth projective varieties in this case. So I should have said, again, we're assuming that the rank and the degree are coprime. So then we will actually get smooth projective varieties here. And I just wanted to remark that so far, actually, all of the motifs of things that we've seen lie inside this category generated by the motif of the curve. But actually, this is not true for the SLN Higgs moduli space. So if we look at the moduli space with fixed determinant, then for a general complex curve, we can show that the motif doesn't lie in this tensor category generated by the motif of the curve. And in particular, we don't have the same situation that we had for theorem A. So the motif of M is not isomorphic to the motif of ML, tensor the motif of the Jacobian. And so in fact, this was already known on the level of cohomology, but it's also true motivically that the gamma n action on the motif of ML is non-trivial. So then together with Liu-Fu, we also proved some explicit formulae in rank 2 and 3 for coprime degree. So let me just present these formulae and then I'll say a few words about the proof. So in rank 2, we actually get an isomorphism which holds with integral coefficients. Although the problem is that we actually only know the motif of n with q coefficients. So really to say more than this, you would need to prove something about the motif of n with the q coefficients. And again, we see the sort of usual things appearing. So we have the Jacobian of our curve, and then we have motifs of symmetric powers of C. And then in rank 3, the Higgs moduli space has motif. So again, from the Bielaniki-Borula decomposition, we get the motif of the moduli space of semi-stable vector bundles, and then we get various other contributions. So we get the Jacobian, and we get some symmetric powers, or in fact, actually products of symmetric powers and some Tate twists, which again, so the index sets here are all written down in our paper, as well as the Tate twists, but just to write some nice formulae in this talk, I haven't bothered to write them out all precisely. And this actually generalizes results of Hitchin in rank 2 and Gothen in rank 3. And so I just wanted to sketch the proof. So the idea is just that we study the BB decomposition associated to this scaling action. So as I said, we get that the fixed locus decomposes the moduli space of semi-stable vector bundles and then various moduli spaces of chains. And where actually, so again, with chains, there's different notions of semi-stability, but there's a particular Higgs stability parameter for chains, and that's the one that you use. And so via the motivic Bielaniki-Borula decomposition, we actually get that the motif of M is the motif of, so basically all of these fixed components with various Tate twists. And in low ranks, we can actually analyze what types appear, so the ranks and the degrees of the chains that we see, and describe the motifs of the corresponding chain moduli spaces. So in rank 2, this really goes back to Hitchin. There's two possibilities. Either, so we have a chain just consisting of one vector, a bundle of rank 2, so not really a chain, actually a vector bundle. So then we get our vector bundle moduli space. Or we have a chain consisting of two line bundles. So we have L0 a line bundle and L1 a line bundle, and the Higgs field sends L0 to L1 tensor omega C. Then these chains of type 1, 1 are parameterized by a, well, basically a Jacobian, so a Picard scheme, and a symmetric power of the curve. So then basically you see the formula, maybe I'll just scroll up, sorry, a tiny bit. Then you see this sort of formula here that we have the Jacobian, and we have a particular symmetric power of the curve, and then a Tate twist, which is just giving us the codimension. And actually there's only finitely many possibilities for the degrees because of stability and the fact that the Higgs field is non-zero. But these possible degrees were actually worked out by Hitchens, so we didn't really have much work to do. It was just to check that this motivic BB decomposition works. Okay, then I want to say a few brief words in rank 3. So because this also relates to pairs moduli spaces. So in rank 3, again, we get the moduli space of semi-stable vector bundles. We also get this type 1, 1, 1 now, where E decomposes as a sum of 3 line bundles, L0, L1, and L2. And this is parameterized now by, so basically we have a Picard scheme, and then we have 2 different symmetric powers of C. And then there's 2 other possibilities, which is that E decomposes as a sum of a rank 2 bundle and a line bundle. And these are kind of dual to each other. So let me just explain the first one. Oh, I see there's a long question in the chat, but maybe I can answer it at the end because I don't have much time. Is that okay? I just don't even have time to read it. Yeah.
Sure, you can answer it in the end. Okay.
Okay, so yeah, let me talk about the type 1, 2. So then we've got a line bundle going to a rank 2 bundle. And then actually by tensoring by L joule, we actually get a rank 2 pair. So remember, a pair is a vector bundle with a section. And so again, we see these pairs moduli spaces appearing. And so again, we can compute their motive by this pairs wall crossing using explicit flips, as in the proof of theorem B. And this is the difference here, that because we have to basically cancel some parts of the motive, we only get a formula with Q coefficients as opposed to Z coefficients. Okay. Yes, so I quickly wanted to explain what happens for the SL Higgs moduli space. So when we fix the determinant. So in this case, we also get a motivic Bielaniki-Berula decomposition, which is actually the one that, so actually when Hitchens was looking at it originally, he was really looking with fixed determinant. But now we get certain étale covers of symmetric powers of curves, which are coming from, basically we need to take a root of some line bundle. And the point is that now you can actually show that the motif of the Higgs moduli space with fixed determinant lies in the tensor subcategory generated by the motif of this curve C tilde. So when J is equal to 1, obtained by this étale cover over the Jacobian. And if you've got a very general complex curve, then this category is strictly larger than the category generated by the motif of the original curve C. And so this is a special feature that seems to happen for this Higgs moduli space. Okay, so in the remaining 15 minutes, I want to talk about parabolic vector bundles and Higgs bundles. So let me just remind you of my notation. So N alpha is the moduli space of parabolic vector bundles, and M alpha is the moduli space of parabolic Higgs bundles. So let me explain what these are. So if we fix a collection of parabolic points on C, P1 through to Pn, then a quasi-parabolic bundle on CD is a vector bundle on C, together with flags in the fibers of each of the points in our set of parabolic points D. And so these flags don't necessarily have to be full flags, although often for simplicity later on in the talk, I'm going to assume that they are. So they have some invariants. So firstly, the length of the flag is one invariant, and then basically the dimension of the successive quotients is what we call the flag multiplicities, and this is another invariant. And then, sorry, And then going to Higgs bundles now. A Higgs bundle is just a quasi-parabolic vector bundle together with a Higgs field, which is a strongly parabolic map. So, well, it's not too important what strongly parabolic means if you don't know, but I've just written it here. But it's just somehow a natural notion of morphisms between parabolic vector bundles. Okay, then we say that so firstly in the non-Higgs case, the parabolic vector bundle is semi-stable with respect to a stability parameter. So this stability parameter, we basically have one positive number for each point in each flag. If for all subbundles, we have an inequality between slopes, where the slope is calculated with respect to this stability parameter. So what does it look like? Well, you have the degree over the rank as usual, but then you have some other factor which involves these stability parameters and the multiplicities. And to calculate the multiplicities of the subbundle, you just intersect your given flag on E with the subbundle, and then you get these multiplicities. Okay, so let me explain the moduli spaces. So there are two different moduli spaces. Firstly, we have the moduli space N alpha. So often I'm just going to write N alpha for shorthand. This is the moduli space of alpha semi-stable parabolic vector bundles of fixed rank, degree, and multiplicity. And this is a projective variety. I've written down its dimension, which is actually just the dimension of N itself. And then for each point in D, you get a dimension of a flag variety associated to the multiplicities at that point. And then also we have the Higgs version. So M alpha is the moduli space of semi-stable Higgs bundles of rank N, degree D, and with multiplicities M. And now this is also a quasi-projective variety. And again, it's very close to actually being a projective variety. So you also have this semi-projective scaling action on the Higgs, the parabolic Higgs moduli space, which actually implies via the motivic Viola-Dicke-Bernoulli decomposition that you can consider the motif actually living inside the category of Chow motifs. And both of these are smooth when semi-stability and stability coincide, so for generic choices of alpha. And so actually, I want to explain two results about basically understanding how the motifs of these two different moduli spaces vary as alpha varies. So we're going to see that they really do change in the vector bundle case, but actually in the Higgs bundle moduli space case, the motif is always the same, so it's independent of alpha. Okay, so for this, we have to talk about variation of stability for parabolic vector bundles. And so what does this look like? Well, first we fix the invariants. So we fix the rank, the degree, and the multiplicity of our parabolic vector bundle. Then in the space of stability parameters, there's some walls, which is where semi-stability changes. And these walls are determined by invariants of subbundles. So they're the alpha for which when we look at the alpha slope with respect to eta prime and eta, they're the same. And I should say that this wall is also the same if you look at the invariant of this sort of quotient bundle. So you get the same wall when you look at the invariant of the quotient. But if we assume that we have full flags, so that's saying that the multiplicities are always one, so the dimension of each vector space in your flag is increasing by one at each point, then each wall basically is determined by a unique pair of invariants, eta prime and eta double prime. And this means that wall crossing is quite nice to describe. So at a single wall, so we're looking at some wall here, and I take a point alpha on this wall, we basically split our space into a positive and a negative half space. So the positive half space is where alpha, when you look at the slope of eta prime and the slope of eta, this is actually greater than 0, and then conversely you also have the negative half space. And then let's take an alpha plus and an alpha minus lying on the positive and minus half spaces. Then there's actually a standard flip again, with center being the moduli space of strictly semi-stable things on the wall, which actually decomposes as a product of two moduli spaces. And then the type of this flip is, so remember we have projective bundles over here, and these projective bundles are basically given by looking at whether you can take an extension from the invariant corresponding to the sub thing and the invariant corresponding to the quotient thing, or flipping them. So you get two different projective bundles, which basically you flip these, whether you're considering the sub-object as a sub-object or a quotient object, and you can explicitly calculate the ranks of these. So I've written it down in terms of some parabolic Euler characteristic, but you can actually write it down really in terms of all of the invariants. I just haven't done so because it will look a bit messy. So then using Zhang's formula, we then get that we can relate the motive on each side of the wall. So we have that the motive on this side of the wall is, and then we have some contributions from the center of the flip with various Tate twists, and then the motive of the parabolic vector bundle moduli space on the right-hand side, and again, some contributions from the center of the flip and some Tate twists. And I should point out that at least one of these sums is non-empty. So although I've written n plus and n minus, I'm not saying that n plus is bigger than n minus. I don't know which way n plus and n minus, I don't know which one is bigger than the other. It sort of depends how you're looking at it. So one of these two sums will be 0. So either the motive of this is bigger or the motive of this is bigger, or actually you could have that actually this is a flopping wall, and so actually both sums disappear. And then using this, we actually show that if you take a fixed integer, natural number even, then provided the genus is sufficiently large, and this how large depends on the I and the invariant that we choose, then actually the ith Chow group of n alpha and n beta are the same when alpha and beta are generic. So this you need to take G sufficiently large, essentially because these grow linearly with G, and so you want to sort of make sure that the Tate twists that you're looking at are sufficiently large. Okay, so then we could ask, well, can we compute the motives of these parabolic vector bundle moduli spaces? And the key here is actually to use flag degenerations studied by Bowden and Yokogawa. So here I'm going to assume that the rank and the degree are coprime. Then if we take a sufficiently small generic stability parameter alpha, then alpha semi-stability of a parabolic vector bundle is equivalent to semi-stability of the underlying vector bundle. And so actually you get a forgetful map going from the moduli space of parabolic vector bundles to the moduli space of vector bundles, which is a flag bundle. And so you can compute the motive of this from the motive of this when alpha is very, very small. And then the idea is to proceed from there via wall crossings. So we actually managed to do this in rank 2. So let me give you some explicit formulae in rank 2. And so we're going to take n parabolic points, and we're going to take full flags at each of these parabolic points. So then without loss of generality, we're actually going to assume that the first parabolic stability parameter is 0 at each point I, and then the second one will lie in 0, 1. And so actually our space of stability parameters or weights is just the interval, the open interval 0, 1 raised to the power of n. So we have one choice for each point in a set of parabolic points D. And there's various symmetries that act on this space. So firstly, we can perform Hecker modifications. So if we take a subset of parabolic points, then we can take, then we get actually an isomorphism by performing a Hecker modification at each of these parabolic points successively. And then that changes the degree by the size of this set. And if this cardinality has, if this set D prime has cardinality which is even, then by tensoring with a line bundle of the degree E, where this has size 2e, we actually get an isomorphism between parabolic vector bundle moduli spaces with the same invariant here. So we've managed to keep the invariant the same, but the stability parameter changes. And so actually we get an action by Hecker modifications on this space of stability parameters, this space of weights here, such that any two stability parameters in the same orbit correspond to isomorphic moduli spaces via these Hecker modifications. And then there's another action, which is the natural symmetric action, which does not give isomorphic moduli spaces, but it does preserve the numerical type of the flip, so this n minus and this n plus. And so it's quite useful for computations. So I wanted to give some pictures for low values of n. So firstly, if we take two parabolic points, so then this is something I can draw relatively easily. So we just have a square here. And in fact, there's only one wall. So it depends whether d is odd or d is even as to where the wall is. So when d is even, the wall actually goes through the origin, which is what you should expect, because the origin is corresponding to the moduli space of semi-stable vector bundles roughly. And we know that then semi-stability is not coinciding with stability when d is even. And via the Hecker modification, you can go between these two pictures for d odd and d even. And this one wall is actually a flopping wall. So the motifs in all of these different chambers coincide. And it's just calculated using this degeneration formula. So we know that if we're here and we degenerate to here, then we get this forgetful map from n alpha to n, whose fiber is 2 copies of P1. And n equals 3, I can still just about draw the picture, but maybe not quite so prettily. So then we get now a cube. And again, doing a Hecker modification at just one point, this sends us between the case when d is odd and d is even. So let's just look at the odd case. So then the walls give us a tetrahedron. So the walls are in blue inside our cube. And essentially this divides us into different chambers. And the outer chambers are permuted by the Hecker modifications. And then the inner chamber is somehow the biggest chamber. So if we look at a stability parameter in one of these exterior chambers, then we get that the motif is just the motif of n and then the motif of the fiber basically via this forgetful map. And then when we go from an exterior chamber to an interior chamber, so we go inside the tetrahedron, then we get, oh, sorry, I see I've changed my notation. I was going to call it out and in, but then we get that the motif of the interior one is the motif of the exterior one, and then plus some wall crossing contribution. So these are genuine flipping walls, so we really see a new contribution appearing here. And so, okay, that's as far as I can draw, but let me say that in general, this sort of story generalizes. So moving from the exterior to the center of this weight space actually increases the motif, which is quite nice. And you get a flopping wall if and only if it contains the center of this, this cube, this hypercube, and this only happens when n is even. And then you can actually compute the motif when the degree is even using Hecker modification. So you can actually describe it for even and odd degrees. And so we actually get some explicit formulas in rank 2 with full flags at n parabolic points. So we have that the motif of the parabolic vector bundle moduli spaces. So again, we get this sort of the motif of the smallest one, and then we get some contributions from the various flips that we have to do. And these exponents, we have explicit formulae for them, but I haven't written them down. Okay, I see I have 1 minute, but I think 1 minute is enough to basically finish. So don't worry, it might be a little bit quick. But so finally, let's talk about parabolic Higgs bundles. So as I said, we can actually consider this motif to lie in the category of Chow motifs using this scaling action. And we actually prove that the motif is actually independent of the stability parameter. So this is very different to the case for parabolic vector bundles. And the proof is essentially 2 points. So firstly, that Thaddeus showed that these moduli spaces for alpha and beta over a wall are related by Mukai flops. And then we show that Mukai flops between smooth varieties actually preserve Chow groups, and so they preserve motifs. And that's really the idea. So I wanted to say that a few final thing. So actually, over the complex numbers, this result was already seen on the level of Betti cohomology. So in rank 2 by Boden and Yokogawa, in rank 3 by Garcia, Prada, Gotten, and Munoz. And actually in rank 2, again, we have an explicit formula, which I'm just going to put up, but I'm not going to say anything about. So again, it's just a motivic Bielaniki-Barula type computation. Okay, and I'm going to stop here. So thank you very much.
So thank you very much for your talk. Super. And so questions. And maybe we could begin with the question in the chat.
Yes.
So, Vicky, maybe you can address what he says here.
So maybe I can.
Oh yeah, please.
Yes, it's me reading. It's quite small.
Please.
So my question was, I think you mentioned that as a group of the Jacobian acts trivially on the, well, when acting on by tensor on the modular space of vector bundles, it acts trivially on the cohomology.
Yeah.
Does that make sense? So my question was if this is true when this is a group of the Jacobian acts on the modular space of Higgs bundles, if it acts trivially on the Higgs field, or maybe multiplying it by a constant.
No, so this is not true on the level of cohomology on for Higgs bundles, and so I'm not. Maybe someone in the audience can help me out as to who showed this, because
so the action maybe it's explicit, or
so actually there's some recent work of Maulik and Shen where they're really looking to actually try and understand what this action is. So maybe that's like one of the best references for you to have a look at on the level of cohomology, just trying to understand. And essentially, it also comes down to looking at various covers of your curve and looking at moduli spaces on those.
Okay, thank you very much. That's very useful.
Thanks for the question.
And then I guess Lisa Jeffrey has asked a reference for the Meta-Shishatri paper.
Oh gosh! On the top of
this is the classical Meta-Shishatri paper, right? I mean,
yeah, yeah.
I don't really need this.
Oh, okay.
It's okay. I know where to find it.
Okay.
It's in our paper somewhere, but I don't have it handy.
No, don't worry.
Okay, yeah, maybe I can write it in the chat later.
Okay, and more questions? I think David has raised his hand, maybe. Yeah. Go ahead, David.
Yeah, if microphone turns on. Yeah, I had a question about this last part about parabolic bundles. The results that you gave about the structure of the motive are for big enough genus or for any genus? Because at some point you mentioned that you needed big genus for the equivalence of cohomologies in the flops, or
yeah, that was for Higgs bundles. There's nothing about the genus, so this just holds for any genus. But for parabolic vector bundles, there was a result. Let me just scroll up. We have a result that says that the ith Chow groups coincide, but then provided the genus is sufficiently large. And so how large actually depends on the original invariant that we're looking at and actually the particular I that we're interested in. And so the idea here is that we have these various Tate twists, and these somehow depend on the n plus and the n minus, but the n plus and the n minus grow linearly with G. So you just need to make those sufficiently large to get that these Tate twists don't feature, basically.
Yeah, but the general equality of motives does hold for any genus. It's just that when you look at specific I's, then you get that they are equal only when the genus is high enough. Otherwise, you get extra terms from the equality, right?
No, sorry. The motive is not the same for, and so if you look at a particular, any genus, large or small, the motive of the vector bundle, the parabolic vector bundle moduli space really depends on the stability parameter. So in rank 2, I think I wrote it down. So like even in this explicit example, you see that the motive really depends. So you actually pick up some extra contributions.
Okay, yeah, right. Okay. Yeah, no, I was, yeah, okay.
Yeah, and in general, I mean, so actually the exponents here really depend on the alpha. I should have pointed that out. So the formula is really depending on the alpha here. Whereas for the parabolic Higgs bundle moduli space, it doesn't depend on alpha. So this stabilization for large genus, I mean, this was for a particular I, and that was kind of the key thing. You don't get the stabilization on the motive.
Yeah, okay.
Because you would need to choose always the G a lot bigger than I sort of thing, but you need to do that for all I, so.
Okay, right. Thanks. And another question about this stuff, because when you talk about the wall crossings, yeah. You consider the wall crossings for fixed for this fixed eta and eta prime for this topological data at the end of the sub bundles. Yeah. These things describe numerical invariants for the wall, but yeah. Some of these walls might not be realized by actually geometric elements existing there.
That's true, but then on the motive level, you would just get the same motive. I mean, so I guess you could have these fake walls somehow, right?
Yeah. Yeah. So for big G, you can actually prove that that's not the case. For big enough G, you can actually prove that all numerical walls are geometrized, are realized geometrically. Okay. So I wonder in your so relating the motive computation, your motive computation actually computes certain differences when you vary alpha through the system, and you are crossing walls, and you're actually giving modifications and proving that the motive is not the same on both sides of the wall.
Exactly.
So could that be an actual proof that those, so in general, in higher rank, because that's explicitly for rank 2, in which those walls are actually known to be geometric, but might your techniques be usable for actually distinguishing geometrical walls?
Well, I guess so. If you knew that really the motive should change, then there has to be something happening, right? But you can also have flopping walls, which is where the motive doesn't change, but it could still be an honest wall. So I don't think it would be quite enough, because you would want to know the difference between a flopping wall and a fake wall somehow, right? And I don't know how you would see that you can't see that from the formulae.
Okay. And if I can, or if I mean, maybe I can wait for the questions, and maybe then because I think we are. Oh, I can. Okay. So another question regarding this explicit formulae in rank 2. So okay, so the construction seems very explicit for the flips and the construction for this for the structure of these flips and the structure of these senders. So I mean, what's the thing that prevents you to compute general rank cohomology in this case, or at least relate the wall crossings in general rank?
Well, in some ways, one of the first things is that you need to degenerate to your moduli space of semi-stable vector bundles, so without parabolic structure. So you would first need to know the motive of that. So we've only computed that in rank 2 and rank 3. So that's sort of the first obstruction, is because the first step is really that you have this flag bundle over the moduli space of semi-stable vector bundles. So you need to know that. And then I think it's just, I mean, probably it's just combinatoric somehow, that very complicated combinatorics. I mean, you would have to, I mean, enumerating all the walls was relatively easy because we had these very explicit ways of dealing with it. Essentially, we only had one stability parameter per parabolic point. That made it quite easy to deal with. But I don't know what would be the real challenges. I mean, so again, if you took full flags, then I think that the walls would all be kind of nice and easy to describe in some senses, but you would also want to ideally have this really nice structure which we discovered, which was that the motive sort of increases as you go into this cube. And this, I mean, I don't know if that's something to expect in general, that somehow, and then you have some sort of symmetries relating the outsides of the cube.
There should be, because I mean, there's so there's actually a good description of a good enumeration of the walls in any rank, and there's actually a good Higgs action commuting those walls with very known stuff. And it seems to me that the structure that you mentioned about this increasing phenomenon should also be present in higher rank, because you still have this biggest structure in which the farther you get to the middle, the higher codimension you get in the walls. So because you can actually compute the codimensions, and you can compute the expected codimensions, at least in geometric walls. So this type of phenomenon should work in, at least in high genus.
So I think the biggest obstruction is actually then working it out for small values of alpha, because so working out what the moduli space of semi-stable vector bundles.
Yeah, of course. No, I was thinking about the wall crossings more. The formula relating, because at the end this formula relates all the things in the very core of the most generic chamber to the most particular small or concentrated chamber. So that's what I was meaning. That wall crossing phenomena should be. So, for example, do you know if this? No, I mean, I think you just answered it. This increasing phenomena should be present.
Well, yeah, I don't know, but I would expect it. But it's not something we investigated. We just looked carefully at rank 2.
Maybe we should also see if there are further questions. Other people.
Maybe I can ask a question.
Yes, Vivek.
Hi, Vicky.
Hi.
I have a question all the way from the very beginning.
Yes. Did I move up?
Yeah, maybe. Well, my question is about the difference between something sitting inside the ring generated by C and being expressible as a direct sum of symmetric powers. Because how close are those things? And also, you gave formulas for rank 2 and rank 3. Do you know in higher ranks that it is a sum of symmetric powers, but maybe a sum of products of symmetric powers, but no, you don't know the coefficient?
Well, morally, I think that it should be, because so we actually, just with Simon, we gave a formula for the motive of the whole stack of vector bundles, which was just in terms of symmetric powers of the curve. And well, okay, there's the Jacobian as well and Tate-Twist, but just very explicit things. And then you can do a Harden-Arrowsimo recursion on that. The only problem is that the Harden-Arrowsimo recursion basically introduces some minus signs, which you can't deal with. And so you have to then do some tricks to rewrite them as a positive expression. So I would expect so. So actually, if you look at the formulae where we had like one symmetric power of the curve and then two symmetric powers of the curve in rank 3, in general, I would expect in rank n, you would have n-1 different factors of symmetric powers of C. And that's true on the level of the motive of the whole stack. So that's why I expect that.
But strictly speaking, what you have presented today doesn't imply that. Is that correct?
Yeah, no, it doesn't strictly speaking imply that.
I see. Thanks.
Okay. Super. More questions? Actually, I had one myself. So is there a notion of motives that kind of also includes some kind of coherent sheaves on the space that you're working with and would somehow determine cohomology of the space with coefficients in these sheaves?
Well, so I mean, in some senses, so the category DM is built out of sheaves on varieties, but usually sheaves of Q vector space. And I think you're thinking of more interesting sheaves, perhaps. And so
line bundles, for example, would be interesting already, right? I mean, but in general, higher rank sheaves and say symmetric powers of the tangent bond. I mean, all kinds of things that you can imagine.
Well, yeah, I mean, so you always have Chern classes of those, right? I mean, so you can then consider them, I mean, as sort of giving you some homomorphism group, or so, because you can think of the Chow groups as being hom groups in this category of motifs. So you can think of then sheaves or vector bundles or something as giving you some sort of morphism between motifs. So maybe that's the best way to think about it.
Yeah, okay. No, I was just thinking, I was sort of hoping that there was some kind of motive that determines, you know, all the indices or all the cohomology groups, ideally, if one could, of, you know, coherent sheaves over these varieties.
Yeah, that's a lot to ask for.
Exactly.